featuring two very distinguished speakers, Professor M. Ram Murty and Professor V. Kumar Murty. We are delighted to have you with us for this exciting day of insightful talks, interactive mathematical displays, and science exhibitions. I am Ahon, your host and anchor for today's event. Before we begin, I would like to share a few very important guidelines to ensure the smooth running of the event. Please switch off your mobile phones or put them on silent mode. Flash photography is not allowed. A professional photographer has been employed who will be taking the photographs. Moreover, the entire event is being live streamed on YouTube, on IISER Kolkata's official YouTube channel. We request everyone to maintain cleanliness. Littering in the auditorium is strictly prohibited. There are dustbins placed outside the auditorium. Do not bring any food items inside the auditorium. However, water bottles are allowed. Please note that food and refreshments are available outside near the registration desk and will be provided after the event. Keep your coupons safely. Do not lose them. Washrooms are located just outside this hall, both to my left and my right. For accessing them, please exit through the main entrance. There are standees and signages to guide you for the same. In case you need any help at any time, our volunteers are available throughout the venue. Please avoid any chaos. Follow their instructions whenever required. We will proceed with the event presently. We have two very wonderful talks today. The first will be given by Professor M. Ram Murty, who is the A.V. Douglas Distinguished University Professor and Queen's Research Chair at the Queen's University in Canada. The talk is titled The Art of Research. The second talk will be given by Professor V. Kumar Murty, who is a professor of mathematics at the University of Toronto in Canada and director of Lodha Mathematical Sciences Institute in Mumbai, which is titled Reflections on the Computer and the Human Brain. We hope you enjoy and learn from both. With that, let us begin our program. Now, I would like to invite on the stage the head of the Department of Mathematics and Statistics of IISER Kolkata, Professor Koel Das, to share a few words and formally open today's program. Ma'am, the stage is yours.
Thank you, Ahon. A very warm welcome to you all from the Department of Mathematics and Statistics. As the name suggests, we work in the broad area of algebra analysis, geometry, number theory, and differential equations in maths, and reliability analysis, non-parametric statistics, applied statistics, and mathematical biology in stats. Okay, so we have a 5-year BSMS program where you can join right after your class 12, after qualifying our IISER entrance exam. We also have a 2-year mathematics master's program in mathematics, which you can join after clearing our entrance exam. Finally, you can also join our PhD program after you complete your master's. Hope to see some of you present here will become a member of our IISER Kolkata community. Now, let us begin the public lectures. So it is time to introduce our first speaker, Professor M. Ram Murty. Professor M. Ram Murty is a highly respected mathematician and a leading figure in number theory. He is the A.V. Douglas Distinguished Professor and holds a Queen's Research Chair at Queen's University, Canada. Throughout his illustrious career, Professor Murty has received numerous prestigious honors, including election as a Fellow of Royal Society of Canada, Fellow of National Academy of Sciences, India, Fellow of Indian National Science Academy. He is also a Fellow of the American Mathematical Society and the Canadian Mathematical Society. His groundbreaking research has earned him major awards such as Jeffrey Williams Prize, Coxeter James Prize, and the CRM Fields Peames Prize. He has held significant fellowships, including the Kilium Research Fellowship, Simons Fellowship, and the EWR Stacy Fellowship, to name a few. Professor Ram Murty is widely recognized for his contributions to analytic number theory, in particular distribution of prime numbers, modular forms, L functions, sieve theory, and circle method. He has authored numerous books and papers, and his work continues to shape the mathematical community. He is deeply committed to teaching and mentorship, supervising numerous graduate students and postdoctoral researchers worldwide, and continues to inspire both students and researchers all around the world. I now invite Professor Ram Murty, our Director in Charge, Professor Rangit Bhattacharya, Dean of International Relations and Outreach, Professor Debashish Kole, and Associate Dean of International Relations and Outreach, Professor Anirban Banerjee, on stage for the felicitation ceremony.
What do we do?
You will present a bouquet. Thank you, Professor Bhattacharya, Professor Kole, and Professor Banerjee. Now let me introduce the second speaker, Professor V. Kumar Murty. Professor V. Kumar Murty is an internationally respected mathematician renowned for his contributions to number theory, arithmetic, algebraic geometry, and information security. He is a professor at the University of Toronto, Canada, and a senior fellow of Massey College, and serves as a director of Fields Institute as well as the director of the newly formed Lodha Mathematical Sciences Institute. Professor Murty has received numerous distinguished honors over his career. He was awarded the Coxeter James Prize and was a fellow of Royal Society of Canada. He, along with Professor M. Ram Murty, received the Ferran Sunyer I. Balaguer Prize for their book Non-Vanishing of L Functions and Their Applications. His accomplishments have been further recognized with the Jeffrey Williams Prize, University of Toronto President's Impact Award. Most recently, in 2025, he was appointed to the Order of Canada, one of the country's highest civilian honors. He is also a fellow of the Fields Institute and a foreign fellow of the National Academy of Sciences, India. A leading figure in contemporary number theory, Professor Murty's pioneering research and dedicated leadership continues to shape the mathematical landscape and inspire scholars worldwide. I now invite Professor Kumar Murty, our Director in Charge, Professor Rangit Bhattacharya, the Dean of International Relations and Outreach, Professor Debashish Kole, and the Associate Dean of International Relations and Outreach, Professor Anirban Banerjee, on stage for the felicitation ceremony for Dr. Kumar Murty. Thank you, Professor Banerjee, Professor Murty, and Professor Kole. Can I now request our Director-in-Charge, Professor Rangit Bhattacharya, to say a few words about our institute? Thank you.
Thank you, Kuel. Good morning, everyone. Professor M. Ram Murty, Professor B. Kumar Murty, and our other faculty members and distinguished guests, and most importantly, the students from school who would listen to how our two distinguished scientists, they will share their views and some of their works and, with you. Now, about IISER Kolkata, I would like to mention a few things. In IISER Kolkata, we offer 6 academic programs which you might find some interest in. So there are 2 BSMS dual degree programs that after immediately completing your +2, you can get admitted to. So we have our own exam, IIS year aptitude test. And in that exam, it's a national exam in 4 subjects, physics, chemistry, mathematics, and biology. And if you qualify, you will be allocated to one of the IISER. We have 7 IISER Kolkata, Pune, Mohali, Bhopal, Trivandrum, Berhampur, and Tirupati. So in all IISER, among many other programs, the BSMS program is our flagship program. So we have in multiple majors like physics, chemistry, mathematics, biology, and art sciences. And very recently, some IISERs, we started computational and data sciences, so that you will find maybe very interesting. So this is one part about the IISER Kolkata. And in IISER Kolkata, you are familiar with some of it, but the most important part, what defines IISER Kolkata as far as the teaching goes for students, that we try to maintain an interdisciplinary approach. So you do not learn just one subject, you try to learn multiple subjects, and that gives you a very broad horizon. Okay. Now, I will not go on about this. You will find most of the information in our website. I welcome all of you, and it's going to be a very wonderful experience. Thank you very much, professors, for joining us, and thank you, everyone.
Thank you, Rangit. So now, without further ado, let us begin our first public lecture. So can I now request Professor Ram Murty to please come on stage.
Thank you very much, Professor Das. Thank you, the Department of Mathematics. Thank you, IISER Kolkata, for the invitation to speak here. I see a lot of youngsters. I hope this talk about the art of research, the art and science of research, will stimulate your minds to pursue a career in research. So let me, oops, why is this not working? Oh, okay, it's good. But my thing is not changing on the screen here. It's changing over there. Could you see why it? Should I close it and open it up again, or see? It's not changing. So let's close it. Should we close it? Let's just say don't save. And, try it again. Maybe it was on for too long or something. All right, so we could try this with the current slide. Yeah, I think this should be the better. Hopefully it'll come. It's now showing up on my thing, but okay, good. All right, thank you, yeah. Okay, thanks, yeah. Okay, so this is showing up, okay. So let me say that all the wisdom that you need in life is in this cartoon. So this is a famous cartoon. It's about the blind man and the elephant. The fabled story of the blind man trying to figure out what an elephant is, applies to many situations in human history, and particularly to the process of scientific discovery. The wisdom contained in this cartoon is not only limited to science, as I will try to illustrate in this talk, but it's actually essential for daily affairs and interpersonal communications. So this is a case where all the scientists, whether their disciplines are mathematics, physics, chemistry, biology, medicine, and so on and so forth, are trying to figure out the mystery of the cosmos in many ways, the mystery of the human being, and each person gets part of it right. But some mind is needed in order to put the whole thing together and unify the process. So we are actually the mystery. In trying to understand anything, we use our own mind. So what's the instrument for knowledge? The human mind. So we have to know how to harness the energies of the mind in order to gain knowledge. So research literally means to re-examine things carefully so that we can discover new things. The human race today has evolved today where it's through cooperation rather than competition. So if Darwin's theory of evolution emphasizes the law of competition, it is the law of cooperation that will take us to higher levels of evolution. So science in particular, and perhaps mathematics even more particularly, is a communal activity, and the results of generations of scientists, both men and women, have been shared and collected, collated for the benefit of the future generations. So this is how science works. Science is a cumulative process. So we must learn how to do research, how to discover, how to explore, and widen our vast understanding. So let me make a disclaimer at the very beginning. The title, The Art of Research, sounds a little pompous. This talk does not claim to give any recipe on how to do research. If there was such a recipe, computers would be able to do it. And at the moment, as you may have tested it, ChatGPT cannot discover anything new. However, there are some general principles that one can apply irrespective of any field. So it doesn't even matter whether you're in the sciences or in the humanities or neither of them. There are general principles of obtaining new knowledge. And so in this particular talk, I'll try to outline and give illustrations from science generally and perhaps more specifically from mathematics. Of course, they'll have a personal bias based because I am a mathematician by training. The basic tools, of course, for research are the mind and the mind's movement in time called life. So, according to the Taittiriya Upanishad, life is meant for only two things, study and teaching. Svadhyaya pravachanabhyam na pravaditavyam. That's the slokam. Do not refrain from study and teaching. So the human being is actually a learning machine, if you want to call it a machine. It's a learning organism. The human being is an organism that is ideal for the purpose of study and teaching. In other words, life is meant for education, and more importantly, it's meant for self-education. So a great sage once said, expressed this beautifully, as long as I live, so long do I learn. Since I'm in Bengal, I might as well tell you who the sage is. It's Ramakrishna Paramahamsa. As long as I live, so long do I learn. And this is the reason that human beings have been endowed with this marvelous instrument called the mind. So this is the great treasure that each one of us carries on the shoulders of ourselves, the human mind. We are carrying a great treasure meant for discovery. So all of us are what we are today because of our mental development. You are here because you trained your mind in a particular fashion, and you got here. So whatever we want to study, the tool happens to be the mind. So we have to know how to use it. Now, the study of mathematics is different from the study of anything else, such as physics, chemistry, biology, and so on and so forth. And the subjects like literature, art, social sciences, history, and so on and so forth. in the following sense. Mathematics, on the one hand, is both an art and a science, and no other subject, as far as I can tell, enjoys this dual status. So the study of mathematics requires a mind that is not only scientific, but it also has to be artistic. And so we not only want to prove theorems, but we want to prove beautiful theorems and have beautiful proofs, whatever that may mean. So we know that beauty lies in the eye of the beholder, so a part of our education has to be learning to see beauty. My definition of genius is, a genius is someone who can see the extraordinary in the ordinary. My definition of stupidity is someone who sees the ordinary in the extraordinary. So the artistic side of research, mental development needed to do mathematics, is different from the mental development needed for the pursuit of other branches of learning in the following sense. On the one hand, we need to have a high order of logical thinking, which is what is cultivated in mathematical training. But on the other hand, we also have to have a high order of the sense of beauty, aesthetic delight. So this talk is about how to cultivate both of these qualities so that for the graduate student or the young students that I see in front of me can learn how to do research and contribute, make a discovery, contribute to the human civilization. And I hope that I will outline some principles that will make this a little bit easier. So this is what I call the art and science of research. So let me begin with what the ABC of research are. What are the essential qualities we need to bring into our mathematical study? There are three. Attention, as you know, is very important. Avadhanam is the Sanskrit word for that. Beauty, anandam. And then adhyayanam, which is classification. Classification, organization seems to lead to knowledge. Organizing ideas seems to lead to knowledge. But you have to observe carefully. So these three qualities are not linearly organized, but they seem to be, they have to be simultaneously developed. So regarding the third quality of classification, the student has to get into the habit of making notes or having a notebook to systematically cultivate these three qualities. So the habit of note-taking is a very profound way of training the mind in organizing thoughts. So the preparation for discovery, the first step is to find something beautiful that you enjoy. Then look at it on the mathematical landscape like the Himalayan peak and gaze at it in wonder and beauty. So appreciation of mathematics is a precursor to doing mathematics. Appreciation of science is a precursor to doing science. Appreciation of music is a precursor to becoming a great musician. You have to enjoy music before you can become a great musician. You have to enjoy science to become a great scientist. So as you gaze attention, you begin to see a path on how to explore it further, and you discover the steps, the classification to climb upwards, and slowly, a certain theory begins to emerge. So let's now discuss the science of research. So research, the essence of research is how to ask good questions. The method of questioning is the way to gain knowledge in all philosophical and scientific traditions. So, but these can't be idle questions or speculations. They have to be meaningful questions. They must be precise and have a singular goal of achieving a greater understanding into the nature of things. And as this is a mental process, it requires energy. Mental thinking requires energy. It requires energy, and also it requires stamina. You have to sustain the process of concentration. And the only description I can find for this process is churning the mind. So you may have figured out the abstract art on my front slide, and it actually has to do with Samudra Manthan. This is a story that appears in the Vishnu Purana. Remarkable story. And it's called Samudra Manthan. I'm sure all of you know it. Let me just remind you in case you don't. The Devas and the Asuras want Amrutam. Now, Amrutam is code in the Upanishads for knowledge, understanding. They want Amrutam, and they realize that they have to churn the ocean, but they have to join forces. It's interesting, isn't it? They have to join forces. So at first, the toxic Halahala appears, and Shiva has to rescue them. This is the Purana. But after the churning, as the churning goes on, it gives rise to all sorts of jewels of knowledge. So how to churn the mind? How to ask good questions. So that's the picture. This is a modern version of the same Samudra Manthan. You see, Kurmavatara, Vishnu in the form of Kurmavatara. Mount Meru is the person on the top. He's being churned by the Devas and the Asuras with Vasuki, used as a rope. And this churning is the process of research. Beautiful idea. So I will present the eightfold way of asking good questions, of essentially churning the mind. The answers, of course, to many questions in life, it goes back to that blind man and the elephant, may depend on how you identify yourself. So if you say you're a number theorist, maybe you'll only see numbers. If you say you're an algebraist, maybe you'll only see the algebra part. If you say you're a physicist, maybe you'll only see the physics. So in some sense, you have to get out of some of these identifications if you want to. So let me just see how you identify yourself. How does that work? So supposing I ask you, what is 2 plus 2? If it's the engineer, he'll take out a calculator and finds the answer is 3.999. A physicist will run an experiment and finds that the answer is somewhere between 3.8 and 4.2. The mathematician says he doesn't know but can show that the answer exists. The philosopher then asks for the meaning of the question. Each person looking at the question differently. And the accountant asks, what would you like the answer to be? So it depends on how you look at the world. So let me begin with the survey method of research. The survey method consists of 2 steps. First, gather facts, and second, organize them. Arrangement of ideas leads to understanding and knowledge. So what is also missing can be revealed. So when you have a clutter of objects on a table and you find that you organize these objects on the table, you'll find what is missing also from the table, right? So in that sense, it's new knowledge. A superb example I want to give you is the discovery of the periodic table in chemistry. So many of you may know about this, but let me tell you what the story is. So you have here Dmitry Mendeleev organized the existing knowledge of the chemical elements and was surprised to find a periodicity in their properties. In the process of writing a student text in chemistry, Mendeleev decided to gather all the facts then known about the elements and organize them according to atomic weight. After struggling, he had a dream, actually. After struggling with it for many days, he had a dream of the periodic table, and he arranged things accordingly. So here's an instance of how preliminary effort leads to an intuition, which sometimes comes through the dream. So an important part of research is the dimension of intuition. We actually don't know how intuition works, but we certainly know that effort is needed before intuition emerges. So how does that work? That's a mystery, but it's worth exploring. Now the periodic table that Mendeleev had discovered sits as a presiding deity in all the chemistry labs. You go to any chemistry lab, first thing you find is this periodic table. Each discovery of a missing element predicted by Mendeleev led to the award of a Nobel Prize in Chemistry. This is an amazing story, right? This organization of knowledge led to a prediction that certain things were missing. You see how he was driven by aesthetics, beauty, a sense of beauty. And this sense of beauty guided him that there has to be this periodic table. He had that intuition in a dream as well. And he made predictions. There has to be an element here. There has to be an element there. And these predictions, every time somebody discovered the missing element, they got a Nobel Prize in chemistry. It's an amazing discovery. So this idea of survey method leads to new knowledge. So the first method. Another method of generating good questions or having idea of research is the method of observations. Careful observations lead to the discovery of patterns, and patterns lead to the question why, opening the door for underlying theory that explains the patterns. You know, sometimes people can even say the essence of knowledge is pattern recognition. The power of the human mind over the robot is pattern recognition. The ChatGPT stuff is just stochastic pattern recognition. It's based on data analysis. But there's something more fundamental in the human mind that can discover patterns very quickly. Even a baby can discover a pattern. A baby can tell the difference between a dog and a cat. ChatGPT needs 1 million pictures of the dogs and 1 million pictures of the cat, and then pollutes the planet in the process of figuring out what is what. This is how. So there's something more fundamental about the human consciousness that all of this raises. Pattern recognition. So an excellent example of the process of pattern recognition is the Michelson-Morley experiment, that the speed of light is constant, independent of any relative motion of the observer. So let's see if this animation works. So this is a stationary apparatus where the clock is stationary, and it's trying to measure the speed of light, and it comes up with a certain measurement. And if the situation is that the whole apparatus is also moving with the light, the idea is the speed of light should be higher, greater than the stationary. But they found that the speed of light was always the same, even in the moving frames. So these two experiments led to a revolution in physics. I'll come back to that later. Combined with this idea is also the message of conjectures. So the Michelson-Morley experiment could not be explained by the Newtonian physics that existed at the time. So this led to the conjecture that there must be a larger theory that will explain the observation. And Newtonian physics took space and time to be absolute and fixed. From the standpoint of the Michelson-Morley experiment, this absolute point of view of space and time was a contradiction. So the startling axiom then is that space and time are not absolutes, that they somehow conspire with each other to make sure the speed of light is always constant. What that theory. Now here's an episode which in the theme of conjectures that I want to highlight, the letter that changed the world. So you all know about the story of Srinivasa Ramanujan, who wrote this famous letter on 16 January 1913 to the English mathematician G.H. Hardy. And it begins with, "Dear Sir, I beg to introduce myself to you as a clerk in the accounts department at the Port Trust Office in Madras. On a salary of only £20 per annum. I'm now about 23 years of age." And then the rest of the letter goes on with 10 pages of theorems. Perhaps the most famous one is this startling equation that the sum of the natural numbers 1 plus 2 plus 3, etc., is equal to minus 1 over 12. Anyone who sees that says this looks ludicrous, but it isn't. And if you want to see some sample, that's Ramanujan's handwriting. So the letter contains formulas like that. Here's more. By the way, that's very beautiful handwriting. And I think it's important for youngsters who I see right here to cultivate penmanship. These days we're all thumbs, right? Pressing. So we're not using the Gnana Mudra, which is joining the thumb with the index finger. And that's what you do when you write. It's a very important idea. So I encourage youngsters to develop writing, because I have faculty members at the moment who can't write cursive. They print. Anyway, enough of my editorial remark, but in the case of Ramanujan, Hardy invited Ramanujan, as you know, to England, and then they had a productive collaboration. The rest is history. You must have seen this movie, The Man Who Knew Infinity, which was shown a couple of days ago here itself, which is a very inspiring documentary movie that was well done. So in the context of Ramanujan's collaboration with Hardy, he came over to England, and in that framework, he made some conjectures. He was studying the coefficients of an infinite product, and he observed some remarkable properties. So let me just give you this formula. This is a product of q times 1 minus q to the n to the power 24, and when you expand it out, you get these numbers called tau n. So Ramanujan went on computing all these numbers. You end up getting the 10th number. And then if you take the 3rd number and multiply it by the 5th number, you end up getting the 15th number. He started noticing these patterns. Pattern recognition, right? Pattern recognition, the essence of knowledge. So he ended up making these famous conjectures. First, that this function is multiplicative whenever m and n are coprime. He also noticed that they satisfy a second-order recurrence relation, something like the Fibonacci sequence. And then he made the 3rd observation that tau of p was always less than 2 times p to the 11 halves. These things have been called the Ramanujan conjectures, and they changed the course of 20th century mathematics, these conjectures. These conjectures led to the development of the theory of modular forms, and now the emerging theory of mock modular forms. This is based on Ramanujan's last letter from his deathbed, where he outlined a new theory of mock modular forms. So it's amazing. He had 2 letters. The first was the opening letter, and the last was the last letter as he was dying. So these 2 letters really changed the course of science. I say science because now I'm told that the theory of mock modular forms is essential for the understanding of the topology and gravitational fields emerging out of black holes. So it's an important idea. Now, observations and conjectures kind of go hand in hand. And they always lead to the development of a rapid development of the field. So an excellent example is, of course, the idea of coin tossing. Now, we all toss coins, heads or tails, and you expect half the time to be heads and half the time to be tails. So the question is, can you make that mathematically precise? Not just roughly half, roughly this. This is a question that De Moor and other people asked in the 17th, 18th centuries. And what is remarkable is that if there is one integral, if you know integral calculus, one integral that changed human civilization, it is the probability integral. So, that's the probability integral that you have. So that, if I had to say what changed human civilization, that one did. Because that is responsible for many, many things. In fact, the controlling of pandemics, hypothesis testing, clinical trials, which drug is better than which drug for curing a disease, is all done by the normal distribution, hypothesis testing. Okay. So the coin tossing is a simple thing that we all see. If you flip a coin 100 times, you expect half the time, 50 times, heads. and 50 times tails. But if you do run the experiment, you're not going to get 50-50. You'll get maybe 48 this and 52 that. So try the experiment. These are called Bernoulli trials. And can you make this precise? And you can. And if you write it out, I'm just going to kind of flash this very quickly. So if you write it out and ask for the expectation, you will see that on average it's 0. It's half the time both happen, but there's a standard deviation of square root of n. And when you try and plot this picture, you will see that it moves into the normal distribution automatically. So it's not exactly half, but it's around a half the time. And the standard deviation is a fact that can be made into a mathematical law, and that's the central limit theorem. So you see this empirical observation, conjecture, theory. So here, the theory is probability and statistics. So finally, you can prove this very rigorously. So this is the idea behind much of this calculation. And where did it start? Coin tossing. Such a simple thing like a coin toss leads to probability theory and statistics. So the central limit theorem is the big deal. So let me just point this out. The central limit theorem was a discovery that took 200 years to make. And finally, you end up with this probability integral, which I will not explain in detail. But if you want my slides, you can have that. But that's basically the probability integral. So you see, this is the integral that changed human civilization. A fourth method of generating questions is what's called reinterpretation. This method of research examines traditional concepts and tries to look at them in a new way. Such a method does not negate past understanding, but expands it and sees it as a special case of the larger phenomenon. So let me now return to the Michelson-Morley experiment. We already observed it carefully, but we didn't have a theory to explain it. So if you change your axioms, you will find that you can start answering the question. So we have to change our notion of space and time. They're not absolutes. And the person who had this brilliant idea was, of course, as you all know, Albert Einstein. And Einstein's special theory of relativity postulates that time dilates and space contracts in order to ensure that the speed of light is constant, irrespective of the frame of observation. So his theory reinterprets space and time. They are not absolutes, nor are they independent. They are interdependent. That's why you call it space-time with a hyphen. And his big idea is gravity is actually curvature of space. So Einstein's theory led to a new view of gravity, not as a force of a pull or a pull, like Newton thought of it, but as curvature of space. So if you have a heavy object, space is like a trampoline type of thing. It kind of pulls the thing down and curves the space. And the planet moves according to the grooves on the surface. So from that perspective, one of the predictions of Einstein theory was that light has to bend due to gravitational fields. So this is a case in point. And Subramanian Chandrasekhar at the time in the 1930s also noticed this phenomenon. And he noticed that if you have a very heavy star and it collapses, it will generate singularities of the form, which we now call black holes. So he predicted that these things have to exist. So how does light bend due to gravity? Well, if you have these massive amount of objects, the light will then be bent, and you can test this. You can test this from the perspective that if the sun is blocking a particular star, we should really not be able to see it if everything is moving in straight lines. But the fact of the matter is, they did experiments in the 1930s and showed that indeed light is bending due to gravity. So it's a proof, corroboration for the theory of relativity. So let me come back to something that all high school students know, that every natural number can be written as a product of prime numbers in a unique way. And I want to look at that in a different light. So here's a cartoon. It says, Research Institute, unanswered questions this way, unquestioned answers the other way. Sometimes we get caught in dogmas, right? We are provided answers. religion, for example, is most of the time. You are already provided answers, and you never are allowed to ask questions. But so the idea of trying to reinterpret is asking questions, try to see familiar things in a new way. So let's take the well-known theorem of unique factorization and try to look at it in a new way. Is there a reformulation that leads to a higher understanding? And this was done by Euler in the 17th century. Euler discovered that there's another way. So you write down all the natural numbers and take the nth powers. This is called the Riemann zeta function. Just write it all down like that. And then since every number can be written as a product of prime powers, uniquely you get this factorization of the infinite series as an infinite product over prime numbers. And this formulation opens the door to study prime numbers from a new way. So even though we knew about unique factorization from a classical Euclidean perspective, the idea of Euler opened the door for a new way of looking at it. And actually it's very important because I'm going to come back to those conjectures that Ramanujan made. So Ramanujan also made these conjectures. So he noticed that his function tau n also has these Euler, what are called Euler products. And the first two Ramanujan conjectures actually can be formulated as saying that these two series are equal. And so the first two conjectures, I told you Ramanujan made three conjectures. The first two conjectures were proved by Mordell in 1917, but it was Erich Heckel, 1936, gave a theoretical basis, but the third conjecture took a long time to prove because it was very deep. It involved algebraic geometry. It still does, unfortunately. There's no way of doing this without algebraic geometry. It was solved by Deligne in 1974, and he got the Fields Medal for this, which is the analog of the Nobel Prize in mathematics. So fifth method of generating questions is the method of analogy. So this method of analogy detects similarities between two seemingly separate ideas and tries to find the underlying theme from which to view both. So for instance, we see some similarities between the Riemann zeta function, Euler's product, and the Ramanujan product. We see that these two are similar and these two are similar. And the question is this part of a general picture? And the answer is it is. It's what's called the Langlands program, which I'm not going to describe, but I'll kind of dance around it in this talk. A sixth method of generating questions is what's called the transfer method. The method of transfer is to take one idea in one field and transport it into another field. So in one aspect, it's to look for applications, whether in the theoretical realm or the technological realm. An example is provided by coding theory. In the 1950s, a fundamental problem was how to deal with errors in the transmission of a signal from a satellite. And this was first addressed by Claude Shannon in the 1948 paper called The Mathematical Theory of Communication. And it's a nice paper, by the way. I would recommend the youngsters, all of you here are capable of reading that paper. It's a beautiful paper to read, and I'm sure you'll be able to make new contributions to this. One of the important ideas that emerged from that is what are called Reed-Solomon codes. I don't know if you know this or not, but every time you go and buy your pizza or whatever you're buying, you have that QR code that you're scanning and paying. The QR code is built out of Reed-Solomon codes. See, and the idea is that even if you fold your boarding card, that QR code that's on that boarding card, even if there's a crease in it, it can still scan it. This is what's called error-correcting codes, that even though some information is missing, this code can recover it. A big idea, very big idea, basic mathematics. Basic mathematics has to do with, well, I'll just flash it very quickly. It has to do with what's called the theory of finite fields. And you take a polynomial and you use you create a particular polynomial and use generators and then of that field and transmit special values of the polynomial at various points. And then famous theorem of Lagrange, which is a famous classical theorem in pure mathematics, turns out that you can retrieve the message. So every time you are buying something with your QR code, you're using basic number theory in the form of Reed-Solomon codes. It's called coding theory. How are you carrying so much information in your pocket? You know, these memory sticks or CDs or DVDs or whatever. How are you compressing data? Coding theory. See, so these are all aspects of coding theory. So the idea is now in satellite transmission, cable television, all forms of digital media, it's the essential idea behind all these forms of data compression and the QR codes is this idea of theory of finite fields. So it's a big idea. So to say that number theory is useless, no, number theory is running the show. A seventh method of generating questions is induction. So induction is really a method of generalization. The most familiar instance of this is, of course, mathematical induction, which I think it was discovered, frankly, in India, ancient India, in the works of Aryabhatta in 500 CE. He has these formulas. He noticed that 1 cubed plus 2 cubed is 9. 1 cubed plus 2 cubed plus 3 cubed is 36. These are all perfect squares. So in general, if I take the sum of the first n cubes, is it always a perfect square? And the answer is yes. You guess it has to be n times n plus 1 over 2 squared, and you can prove it by what's called mathematical induction. So a more interesting illustration is given, I'm going to come back to that example of Ramanujan's again, given by L functions. So the hierarchy of L functions, so what happened, if you go back now, see what Euler did, what Ramanujan did, and what Langlands and other people were doing afterwards, we see that there's a hierarchy of L functions. So they found the tip of the iceberg, the famous Langlands program, and the roots go back to Hecke's generalization of Ramanujan's work, but then you need the representation theory of Harishchandra. So here are the people. So that's Hecke at the top, Harishchandra in the middle, and Robert Langlands. And so these three people, in some sense, together, if you put their works together, you come up with what's called the Langlands program. And I think some of you may have heard of this. Fermat's last theorem was solved using the theory of L functions, and it's a culmination of human ingenuity spanning over 350 years. It's an amazing idea. Yeah, it's a beautiful thing. So finally, let me say that what's called the converse method is another method of generating questions. So every time A implies B, you can ask the question, does B imply A? And this process leads to new knowledge. In fact, it may change the world again. So the question often leads to profound discoveries. An example is given, my favorite example is electromagnetism. It was known in the 19th century that an electric current creates a magnetic field. And so the question was whether a magnetic field creates an electric current. And the person who asked this question was Michael Faraday. And he is now credited with the discovery of electromagnetism. Interesting, isn't it? And the human body is an electromagnetic field. You're all generating electromagnetic fields around you because you are a bunch of electrical wires called nerves. So the electromagnetic world is a world that we live in. So let me now summarize what I've said. I said the essence of research is to ask good questions. And then I gave you 8 methods of asking good questions. So what were they? Well, they are survey method. Remember Dmitry Mendeleev? Organizing knowledge and putting it together all of a sudden makes this big discovery. Observations, Michelson-Morley experiment. Conjectures, Ramanujan conjectures. Reinterpretation, Einstein with his theory of relativity saying that space-times are not absolute, but gravity is actually curvature of space, so it's a reinterpretation of the Newtonian view of the world. Finding analogies, so something is happening here, something similar must be happening here in a different world, and pushing that. The transfer method, so an idea that was successful in one field can be transplanted into another field, and then you get a new idea. The induction method of generating questions by seeing special cases and then seeing a general pattern. And finally, if A implies B, does B imply A? I gave the example of electromagnetism. So if you didn't take notes, but were lamenting the fact that you should have, there's no need. If you look at the first couple of the letters, you will see that it spells out Socratic, which is the method of questioning. So, with the power of scientific research, we have been able to look very far into outer space. Here is the, let's see, why is this moving? Yeah, okay. So this is how far we have been able to look out into outer space. This is the Coma cluster of galaxies. This was photographed by the Hubble telescope. That's amazing. Sitting, a lonely insect on the planet Earth called a human being has been able to look out into the farthest stretches of outer space using the only instrument he has or she has, which is the human mind. So, the past is ever present. We are here because of discoveries of countless people from countless countries, countless worlds, countless generations, who churned their mind. Samudramantam. So let us journey inward and ascend the Himalayan peaks and find those gems of great discoveries. So thank you for your attention.
Thank you, Professor Murty, for a wonderful talk. So we have now the floor for questions. So anyone wants to ask any questions, please raise your hands and then we'll come to you with mics.
There's somebody over there.
Over there?
Over there, yeah. If you stand up, it'd be...
Can you please stand up?
Okay. Is it okay?
Yeah.
Take it over. Too late now.
Good afternoon, sir. You mentioned 3 important tools that we need for research, like attention, then ability to see beauty, and the ability of classification. I want to ask you, where does patience sit in this picture? Because I think that is also one very important element in research.
Yeah, absolutely. Patience, right? Is that what you said?
Yeah, patience and lack of impatience, because we have to manage our impatience.
Absolutely. So I gave the example of Mendeleev, Dmitry Mendeleev, who was trying to understand the structure of, all these elements, and he had a lot of patience. He was organizing his thoughts, and he even produced a deck of cards with chemical elements on them, and trying to see, is there some pattern? So this struggle has to be there, but you also have to be patient, and he was patient. And then somehow, in a dream, he gets this vision. So I think what we call visions and intuitions and dreams of inspiration can only be the product of first effort and second patience. So there is that creative, so we wait for the inspiration, certain amount of patience, but effort has to be there too.
Okay, sir. And one more thing, to produce substantial work, what would you say? Like, it is more of breadth of the field that we have to cover, or the depth that matters more for substantial work?
Well, I think in anything it has to be depth first. If you try to be broad too early in the game, you will not have any depth. So the first thing is to have more depth first. And for that, you don't sit around saying, let me make a big discovery. That's not what you do. What you do is find something beautiful, find something you enjoy, and read something just for the fun of it. Okay, and then comes back to your patience, you see. Then just be patient. Inspiration then will come, but that's the ingredient. Those are the ingredients you need first to get the chemistry going.
Okay, sir. Thank you.
Maybe we have time for a couple of more questions. Yeah, so there.
Sir, my question is that can we calculate the human brain consciousness through mathematical analysis?
Very good question. Very
Thank
good
you,
question that you've asked. You know, I have been doing mathematics for a long time, and I have also been interested in philosophy. I have been interested in physics, astronomy, and many other things, neuroscience too. You know, I've been interested in neurology and neuroscience and all these things. I'm somewhat of an eclectic personality. It seems to me that all these different subjects are now converging. So if you look at even physics after the quantum revolution, you find many physicists like Schrodinger and other people who are talking about consciousness. And now if you check people like Penrose, they're talking about consciousness. And now in the context of artificial intelligence and ChatGPT, the claim that computer science or these robots have discovered consciousness is to be now challenged. Is that really consciousness, or is it just some neural network thing? So in the ancient Indian tradition, we have talked about koshas. You know, so the koshas are the Annamaya kosha is the physical body, the Pranamaya kosha is the nervous system, the Manomaya kosha is the mental world, the Vijnanamaya kosha is the wisdom world, and the Anandamaya kosha is beyond that. So we already have. So all I say with the robotic situation is perhaps they have managed to duplicate a fraction of the Pranamaya kosha, the neural networks, you know. So that's how, so to claim that this is now discovered consciousness, it raises this question that you just asked, is there a mathematical theory of consciousness? I would have to answer that question with a yes and a no. If consciousness is the eternal observer, according to Indian philosophy, the idea is the sakshi, the eternal observer. So it is illumining everything, whether they're thoughts, whether they're feelings, and so on and so forth. The light by which you see thoughts, the light by which you see feelings is consciousness. So everything that you look at in the realm of concepts is illumined by the light of consciousness. So can we have a conceptual framework to look at something which lies beyond concepts? Of course, probably not. But you can try. We can try to, because of these various levels, like the Manomaya kosha and the Vijnanamaya kosha still are in the realm of the phenomenal. We could, perhaps there should be a theory, there should be a mathematical theory of consciousness. Yeah, good question.
Thank you, sir.
Maybe we have time for one last question, if anyone would like to ask.
Person here. Oh.
Sir, I would like to ask the fundamental question that could we calculate the existence of ourselves in the cosmos using mathematics? As I prefer imagination in research. Like, for example, when I watched the film 2001: A Space Odyssey, which was released back in the the year 1968, then the director was so much speculative about using the DSLR lens with the negative photography that today VFX producers are so amazed that after so much years, the film's visual effects look still good if it is not made with the CGI, but many people are still. So we could combine the imagination with the research?
Yes, absolutely. That was one of the main points I was making, that imagination has to be married with logic. You see, I tried to explain that the mathematics has both a reason dimension, logical thinking, combined with aesthetic, imaginative thought process. So both have to be cultivated in unison. Yeah.
Okay.
Thank you, sir.
Thanks, everyone, and thanks, Professor Murty. So we end the first lecture. I would like to call Ahon on stage, who will tell you about the next course.
Thanks. Oops. Yeah. Take this out. Yeah.
Thank you, Professor, for such an enlightening talk, and thank you all for participating in the Q&A. Remember, people, Socratic is the key. This concludes the first talk of the event. Before we commence the next talk in 10 minutes, I request the students who have not registered for this event to go to the registration desk outside and get themselves registered. If you are a school student who has not registered, any one person can go on behalf of all the students for the registration process. Why is this necessary? Well, please collect your food coupons, as you will not be able to proclaim the food and refreshments without them after this event is over. In the meantime, I request the technical team to please run the ISER Kolkata documentary.
কি ক্লোজ করবে সাউন্ড ঢোকেনি তো পুরোটা ওকে 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 তোমার ওখানে তো সাউন্ড বাড়াও এটা সাউন্ড দেওয়া সাউন্ড করানো আছে
কিন্তু সাউন্ড সেট কর সাউন্ডে যা সাউন্ডে রাইট ক্লিক কর দিস ফার্স্ট হ্যাঁ সাউন্ড সেটিংস কর এই
হেডফোন
God.
Next generation of scientific leaders through a dynamic and interdisciplinary curriculum.
Established in 2006, the Indian Institute of Science, Education and Research, Kolkata, or IISER Kolkata, the first among IISERs, is a premier institution dedicated to nurturing scientific talent. Nestled on a sprawling 201-acre verdant campus in Mohanpur, near the cultural heart of India, Kolkata, the institute offers a serene environment conducive to academic pursuits. IISER Kolkata's core philosophy revolves around seamlessly blending teaching and research. This unique approach empowers students to not only acquire knowledge, but also to actively contribute to the frontiers of science.
I am proud to say that the current year, IISER is ranking 6th in the top 10 science research institution in the country. For the information, we run integrated BSMS Mass program, Master's program, integrated PhD program and PhD program in basic science disciplines with multiple exits as per the National Education Policy.
Our institute is committed to nurturing the next generation of scientific leaders through a dynamic and interdisciplinary curriculum. In alignment with National Education Policy 2020, we offer credit-based course choice, and this offers flexibility and encourages students to explore diverse fields, ranging from foundational sciences to cutting-edge research.
IISER Kolkata has central facility that contains high-end instrument and excellent infrastructure for research, and that caters the need of researchers, startups, and industries by providing them the round-the-clock access with minimal downtime.
The access and sharing of scientific equipment and infrastructure towards an Atmanirbhar Bharat is to facilitate the creation of knowledge from R&D and applied science towards a developed India. IISER Kolkata's facilities are such as atomic force microscopy, confocal microscopy, field emission scanning, electron microscopy, stimulated emission depression microscopy, transmission electron microscope, isothermal titration calorimeter, single crystal X-ray diffractometer, nuclear magnetic resonance, X-ray photoelectron spectroscopy.
Within a decade, the institute has garnered significant national and international recognition, securing substantial research grants from various funding agencies. This support fuels a vibrant research culture.
Currently, IISER Kolkata is involved in executing around 200 external projects, including 170 projects from government funding agencies, 16 projects from bilateral funding agencies, and 8 projects from industry, with a total current amount of almost 100 crores.
At IISER Kolkata, our research initiatives are strategically aligned with national missions, focusing on critical areas such as carbon capture and sustainable energy, also space science innovations and advanced drug development.
IISER Kolkata is a vibrant residential community of students housed in modern hostels. The institute's state-of-the-art research block and cutting-edge laboratories provide an ideal environment for academic pursuits. Complementing the scholarly atmosphere, the Student Activity Center fosters a dynamic campus life with various sporting activities.
We also complemented by having a lot of cultural and sports activities so that their creativity is surged even after classes and labs and all that, right? So for that, we have like 30 clubs. We have the Students Affairs Council or SAC, which is actually formed by the students themselves.
And we essentially help to manage and review student activities in our institute, and also be the voice of the students to the faculty and other relevant people in our institute.
Our educational institution is committed to the well-being of its students, offering a robust support system that includes comprehensive mental health and counseling services. In addition to mental health services, the institution also houses a fully equipped medical center staffed by qualified healthcare professionals. IISER Kolkata faculty members are renowned for their exceptional teaching abilities and unwavering commitment towards research.
The availability of a small animal research facility at IISER Kolkata is critical to addressing basic biological and biomedical questions in disease biology, as experiments on humans is often not possible. Small mammalian models such as mice and rats are physiologically closer to humans and therefore amenable to large number of experimental interventions.
In addition, IISER Kolkata has set up a top-end high-performance computing clusters named Direct Supercomputing Facility. All the facilities at IISER Kolkata can be utilized by any user or organization on the payment of nominal charges.
Early research support has been instrumental in cultivating a culture of excellence, as evidenced by the faculty's impressive publication records of approximately 2,400 papers in high-impact journals over the past decade.
The best award for the faculties in recognition of their performances in research in this country is known to be the Bhatnagar Award, given by the Council of Scientific and Industrial Research. Professor Soumitra Banerjee, Professor Bishwarup Mukhopadhyay, Professor Shadhin Kumar Mandal, and Professor Rahul Banerjee are the recipient of this award.
IISER Kolkata fosters a vibrant ecosystem for innovation and startups, creating a dynamic environment where ideas can flourish and turn into successful ventures. Through a dedicated incubation center, the RISE Foundation, supported by the DST Government of India, mentorship programs and access to industry networks, we empower aspiring entrepreneurs to bring their innovative ideas to life.
If you see where our verticals are, we are looking at agri-tech, affordable healthcare and biotech, quantum computing, clean tech, climate change. You talk about any of the deep science verticals, and we are trying to help companies, translate these into great technology.
IISER Kolkata students are actively involved in organizing a diverse range of events beyond athletics. The Institute's literary festival, Lexis, has gained significant popularity.
We are entering into the phase B. We are also proposing BSMS in data sciences, which we all understand is going to make a big difference in everybody's life. Overall, I feel that we have achieved the targets, and to me, our future looks bright.
IISER Kolkata envisions a future where it leads in promoting fundamental scientific education, conducting cutting-edge interdisciplinary research, and translating research outcomes into industrial applications through a robust, innovative ecosystem.
Okay, so we are going to begin the second public lecture. I would request all the students to kindly take their seats as soon as possible. Okay, it's my great privilege to now call Professor Kumar Murty on stage to give his public lecture.
May I begin? Yes, okay, very good. So thank you very much for the organizing this event. It's always a pleasure to see a lot of young people. I think one of the great benefits of being an academic is that we have constant exposure to new generations of young people eager to learn, asking questions, because that is the life we enjoy. That is our whole life is about asking questions, asking for answers to problems that haven't been solved, and in discovering those answers, and in sharing those answers with others. So this kind of environment I find very, very stimulating. So thank you for attending. I want to talk to you about a topic that is very relevant, very apropos in the current technological situation that the world finds itself in. We have a lot of big problems. And we're getting, as we tackle these big problems, new tools are becoming available that didn't exist a few decades ago. And these tools are so powerful that they're promising in terms of helping us solve these big problems, but they're also very dangerous. And so we have to learn how to use them carefully and creatively so that they actually help us to create a better world. So obviously I'm talking about things like artificial intelligence, but it's a good time to reflect on this kind of thinking machines that we're creating, computers, and the natural thinking machine that already exists, namely the human being and the human brain. So this is going to be a general kind of discussion about the relationship between those two, the way that these two instruments process information and make discoveries, and how we might utilize them for good in the future. Okay, so firstly, the world has gone through many, many convulsions of what we call disruptive technologies. That is, technologies that change the world or change the way we interact with the world. And it's been happening since ancient times. And each time it happens, we have to ask ourselves, has it made for a better world or a worse world? And the answer is always the same. It's made for both. So if you think in ancient times of the discovery of fire, fire enabled the possibility of, even after the sun sets, to be able to carry on with some activities. But also fire has the danger of harming people and property as well. Then there is the wheel that enabled all sorts of motion, writing, and mathematics, an ancient discovery. Writing especially, it was an interesting comment made by Socrates, the Greek thinker, that he didn't like the whole concept of writing. He felt that with writing, it would be the end of thinking. And you see that sometimes people think because they've taken notes, they've understood something. So Socrates was saying, no, you have to encourage, stimulate the whole process of thinking, and maybe writing or taking notes will actually get in the way of that. Well, partly he's right, because if you just take notes and then forget about it, and you don't think about it, then yes, it's not going to help your understanding. But on the other hand, you imagine, because of writing, we today are able to study ideas from thousands of years ago. So in all of these discoveries, we find, yes, there is something to criticize, something to be careful about, but there's something enabling and empowering also in these technologies. In Middle times, gunpowder was discovered, sea travel. Again, you can answer for yourself how these are both have positive and negative implications. And in modern times, we have all sorts of mechanisms for travel. We have microchips, we have the internet, we have cell phones. Cell phones, are they good or are they bad? Well, if you're addicted to your device, it's bad. But if you're in a remote place and it enables you to get access to important information that is critical for your survival, it's good. So these are the kind of conversations that are happening. And now we have a new paradigm that we're facing. Quantum computing of course, but also AI. I'm not so worried about quantum computing. So far as I know, a real quantum computer doesn't exist yet. A significant quantum computer might not exist for some time. But AI is already here. It's here today. It's having an impact. And so we need to sort of understand what it is in both the positive and the negative light, and especially is it a tool to solve the really big problems that are facing us as a world, such as climate change, global peace, the ability to empower individuals wherever they may be in the world to live a happy and prosperous life. So we have a new phase of challenges and opportunities. I just said climate change, populations, and the whole business of the paradigms of computers and computation and human interaction with these. Now, in this context, there are two drivers that we need to pay attention to. One is data, and the other is mathematics. So my field is mathematics, so you'll see a bias always in my discussion that mathematics plays a role. But I believe these are two fundamental things that we are going to, all of us, have to have some sort of understanding of. So firstly, let me talk about data. So I said data and mathematics. Let's talk about data. There's actually three kinds of data. And the way human beings have been interacting with data has been undergoing a transformation. So firstly, there is the data that science has been studying. Science studies data that already exists. We have a universe, whether it's the cosmos or our planet or our biological functions. We have a universe. There is data that is there, and science studies that data. It comes from the physical universe. But now, since social networks and similar technologies have been invented, there's a new source of data, namely our behavior. Behavior has become a source of data. So if the old study of data was about the physical universe, the current study of data is about the behavioral universe. And there is yet a third frontier of data that is just really at its early stages, and that is the data of living systems, the data of life. There we have our understanding is very primitive still. And disruptive technologies such as AI are pushing us very fast towards that frontier of exploring what is the living universe. What can we as scientists or even as human beings say about the data that is contained in the living universe? Several of the academic leaders here have spoken about the importance of interdisciplinarity, that ICER Kolkata emphasizes the interdisciplinary approach to knowledge, and that's really good because that's exactly what we need. We're asking ourselves deeper and deeper questions that don't fit into any neat disciplinary category. It's not enough to say I'm a mathematician and so I'm the only tool I can apply to solve these big problems is mathematics. If I ask questions, or if you ask questions like, what does it mean to be a human being? It's going to require many different perspectives in order to even attempt an answer to a question like that. We will need the help of not only the scientists, but also the philosophers and the sociologists. I find now, after many years in several fields that I've studied, disciplinary boundaries are just simply too restrictive. The problems that we need to work with are things that will require us to have an open mind about where ideas are going to be coming from. So I would say now, this is a mantra that educational institutions around the world have to adopt. Interdisciplinarity is not a luxury, it's a necessity. It's going to be the way of the future. Now, we'll think about mathematics. How has mathematics evolved? You see, if you're first just beginning on your adventure in mathematics, you may say, what does it mean for mathematics to evolve? Mathematics is mathematics. It was discovered, and now we'll use it for solving different things. But those who are in the field know that, no, the field is evolving, it's growing, it's changing. There are problems that we don't know, we didn't know how to solve a decade ago or a couple of hundred centuries ago, a few centuries ago, and which we can solve now. Why? Because new ideas have been invented or introduced, and they've thrown light on problems that we were stuck on in the past. So the subject certainly is evolving. And part of the stimulation for that evolution is, of course, some of it comes from mathematics itself, but some of it comes from questions that people ask us. When Einstein was trying to understand space-time, he asked the geometers, what is the underlying geometry that will explain space-time? This whole way that hyperbolic geometry developed so fast was because the questions that were being posed to us by the physicists. And similarly now, we are with the movement forward in AI and quantum technologies, again, we're being asked hard questions that are going to require the discovery of new mathematics. Most of the mathematics that is relevant here, so far anyway, has been in linear algebra. You know, how does your Google search engine works? It's linear algebra. Dynamical systems, PD, and also number theory. How do you make secure internet transactions? It's because of number theory. How do you make secure satellite or even satellite communications across hostile environments? It's because of error correcting codes that are also part of number theory. So here's a big question that is relevant both to people outside of the field and to people inside the field. What are the new mathematical opportunities that await us as we understand AI, and more generally, as we sort of start probing the living universe? Okay, this is Eugene Wigner. He's a physicist. He wrote an article which has become very famous. It's called The Unreasonable Effectiveness of Mathematics. So he's talking about how accurately mathematical laws are able to predict phenomena in the physical universe. And he wonders why. Why is mathematics so effective in predicting physical phenomena? So his paper is called, it's not, he thought it's unreasonably accurate. So his paper is called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. So as I said, the statement coming after tremendous success in using mathematical methods in physics. Why is the physical universe mathematical? The answer to that question actually is partly philosophical and partly scientific. The philosophical thing says it's the wrong question to ask. Why? Because there's a hypothesis there in asking the question, asking for a solution to the question of why is the physical universe mathematical. The hypothesis is that everything that happens has a why. Well, that may be true in some situations, may not be true in other situations, but maybe it's the wrong question. And science has evolved a lot from the time of Archimedes to Newton to Einstein to today in trying to ask these questions about how and why. You know, how does something happen? The scientist tries to answer that question. At the time of Archimedes, that was the way one approached science. But already by the time you come to Newton, if you ask, how does gravity work? He said, I don't know. I can't answer the question of how. All I can tell you is the mechanism by which it happens, the mathematical formulation by which it happens, but I can't explain the answer how. And then you come to Einstein, who said, we can explain neither the how nor the why. All we can give you is a mathematical metaphor by which we model what we're observing. And to the extent that that model produces predictions that can be verified, the model is a good model. So the best that our understanding, best understanding we can get is to formulate a model that mimics or simulates the world that we're trying to study, and then use that model to predict what happens and check the predictions for their validity. So this is a question, why is the universe mathematical? Actually, to tell you the truth, we don't know. But it does seem to be, and we use it in predicting physical phenomena. Now, this is Erwin Schrödinger, who was also a very famous physicist. He became famous for his discoveries in quantum mechanics. He is Austrian, and he had to flee Austria. He found refuge in Ireland. And while in Ireland, he was asked to give some lectures. He was already a very famous physicist for his discoveries, the Schrödinger wave equation, other discoveries in quantum mechanics. He was asked to give lectures to the Royal Academy there, and everybody was expecting him to talk about quantum mechanics. Instead, he announced the lectures, his lecture would be called, "What is Life?" Now, when you hear that, the physicist is going to talk about what is life, you say, what is it he's going to say? Is he going to give philosophical speculation about life? Is it, why is the scientist talking about this? So it was a mystery to see why he chose that topic. So people were wondering, what is the meaning of this? So some said, no, life is too mysterious, and certainly a scientist will not be able to capture it in a few mathematical equations and pretend that they've explained life. That can't be it. But really what Schrödinger was asking was a scientific question. He was saying mathematics or even physics and chemistry, physics has been very successful in explaining the physical universe that we live in. Is it possible to use physics and chemistry to explain the biochemical processes that happen in a living organism? So he's asking a scientific question. He's not asking about life in the mysterious sense that we think philosophically or spiritually, but he's just and he was very clear in saying this, he was very clear that the physics and chemistry that existed at that time physics and new chemistry had to be discovered that would make it possible to explain the biochemistry of living organisms. And how do you write the laws of science? The laws of science are written in the language of science, and the language of science is mathematics. That is how science expresses itself. So therefore, new mathematical statements had to be invented, had to be discovered in order to be able to explain the living universe. And he makes a very provocative, very interesting statement right at the beginning of his lectures. By the way, the lectures are published. You can find the book. It's called What is Life by Erwin Schrödinger. And he says the following thing right at the beginning. The subject matter was a difficult one, and the lectures could not be termed popular. You see, when a scientist announces a topic like what is life, you think maybe this is a popular lecture. He's saying, no, I'm going to give a technical lecture. So the physicist's most dreaded weapon, mathematical deduction, would hardly be utilized. Very interesting statement for him to make. So what he's saying there is that they're not popular lectures, they're going to be technical lectures, but I'm not going to use math in the lecture. So you'd think that physicists would be very comfortable with math, but he's saying the physicist's most dreaded weapon is mathematical deduction. When you hear this, when the mathematicians hear this, they're liable to feel very happy that we are the nuclear option. Well, if you know of math, that's it. It's going to put everything to rest. But he says there he's not going to use math. And then the next line sort of punctures our balloon of arrogance when he says that the reason he's not going to include math is the subject. The reason for this is not because the subject is simple enough to be explained without math, rather it was much too involved to be fully accessible to mathematics. In other words, he's saying, if you thought the math in physics, the physics of the universe, living physical universe was hard, the math that we need for the living organisms doesn't yet exist. It's even harder. So therefore, that even math may not be enough to explain the living universe. So, but this is a problem that keeps coming up. Can mathematics be effective in describing the living universe? We've certainly had some success stories, big success stories. For example, population growth is developed a good field that's been developed quite extensively. Epidemiology, mathematical epidemiology was very successful during the pandemic in predicting the spread of diseases. And we also know that because of the increase in computing power, the explosion of data, we can do experiments in simulation rather than in actual fact. That is, biological experiments can be done in silico. So all of these things are there, and they use existing math, but as I said before, they also ask questions of mathematicians, that is, stimulating the development of new mathematical tools. On this effectiveness of data, I want to show you one just tiny example. This is a graph that we drew during the pandemic. Many people around the world were trying to understand how COVID was spreading. How do you, and mainly, of course, there were two kinds of groups that were asking this question. Some were worried about the biochemistry of it. They were trying to develop the vaccine. So that was one group of people. The other group of people were more connected to public health. So we want to know, roughly speaking, what's going to happen next week, what's going to happen next month, because the government needs to know, because they need to put in the public health measures to respond appropriately for whatever is coming. So we had in Ontario, Canada, we had a modeling table, and we had a group of modeling experts meeting every week trying to figure this out, trying to figure out what's going to happen next. During that time, we developed a completely new model that was not based on any existing framework. We called it the hurricane model. And basically, we borrowed ideas from climate science. So climatologists are able to, meteorologists are able to tell you, they're able to predict the path of a hurricane. You know, if a hurricane is coming or forming, they're able to sort of tell you, roughly speaking, which path it's going to take. So we wondered whether we could use those kind of ideas to predict the path of the pandemic, the virus. So of course, we need to modify it, because we're not moving in physical space, we're moving in time. So, but after modification, we came up with a new model called the hurricane model. And we were making predictions. This is a graph that we drew in November of 2021. Unlike all of the other models that people were working on, the hurricane model seemed to be able to see faster and further. So here's a prediction for the next 4 months out from November 2021. And we gave them four possible scenarios of which way it might go. But you see what actually happened, how closely it tracked one of those lines, the so-called 75% line. So we were saying there's going to be growth of, there's going to be rapid growth in the next few weeks. It's going to follow the 75% line. And you see how the data hugs that line. So what is interesting about this is that the hurricane model is very data agnostic. It doesn't probe deeply into the nature of this particular virus or that particular virus. It can be used almost agnostically over any broad set of data. And somehow the data captures exactly what we need to know. So there's a mystery going on in data that is yet to be understood. This is just one tiny example. On top of that, living systems, when we try to understand, because the physicists are asking us, or the Schrödinger is asking us, what is life? People are trying to formulate the mathematical laws governing living systems. We have to understand there are new phenomena that happen in the living world that don't happen in the physical world. And one of them has to do with cooperation. Whether it's at the level of the human organism or even at the cellular level, whether it's within species or interspecies, we tend to help each other. So it's not a case of I will survive at your expense or you will survive at my expense. We try to survive together. We try to cooperate. All of our whole concept of society depends on that. Social organization depends on it. Here in the animal world, this is a squirrel. It's called the bending squirrel. and they graze in communities, and when there is danger, when there's an eagle or a falcon or something about to attack, the squirrel stands up and starts making a noise. Now, it makes that noise to warn its fellow squirrels that there is danger. But by doing that, it exposes itself, because now it's visible. And yet, it does that. Why does it do it? So there is some inbuilt aspect of cooperation amongst the squirrels. And of course, there are many examples with other species like elephants, how they protect each other, protect their young at the time of danger. So there seems to be another aspect in the living universe that we don't see in the physical universe, namely cooperation. So whatever mathematical model we come up with for the living world has to take that into account. I already told you about the pandemic. Here's another thing that we learned in the pandemic. Most of the modelers were using something called the SIR model. That's a particular kind of compartment model that can help us to understand the growth or propagation of disease. By the way, that model, the early antecedents of that started in India with the modeling of malaria growth. Eventually, it evolved into the SIR model, and you've all seen during the pandemic these graphs where they're trying to tell you the number of cases that are coming, and they go up and they come down like this, right? You've seen these graphs. So we were listening to these modelers tell us these graphs, and then I asked a question. You're telling me the graph goes up like this and comes down like this. Why is it never actually comes down? You see, the graph goes up like this, and then you're coming down, and then a second wave starts and you go back up. And then you come down again, and a third wave starts and you go back up. Why doesn't your model see that there are going to be waves? And there was no answer to that question, because the SIR model, the solution decays monotonically. It doesn't oscillate. So what was the answer to that question? Well, we found the answer during the pandemic. The answer was that there are actually two viruses. There's the biological virus that everybody was observing. There's a second virus of fear. And when you include that into the model, then the waves become obvious. The wave actually appear. What am I talking about? I'm saying, in simple words, it is like this, that when the cases start coming down, and it's reported that cases are coming down, people think, oh, okay, it's all over, it's fine, we're safe. They lose fear. They say, no, it's okay, we're safe, we can start. We start mixing, what happens? The cases start multiplying again. It goes up. And then when they go up, then we become afraid, and we all mask, we do physical distancing, and the cases start coming down again. So the point is that we have to take behavior into account when we're doing these models, and that's missing from the SIR model. So when you take that into account, then we understand this. And now this has become a field. Behavioral epidemiology, behavioral mathematical biology is now an important field. So again, I'm telling you that in the living universe, it's not enough just to see the physical phenomena. You need to take into account something about human behavior. But not just human behavior, living behavior. And I told you about trust. We did an 11-country survey, 20,000 people around the world. We asked them, if you are told that if the government tells you this is the public health guidelines, you're supposed to mask, you're supposed to physically distance, will you do it? That was the question. Or what is that, whose opinion would you trust in deciding whether you would do it or not? And we found consistently across many countries, the answer is they trust their community. So what their community says, that's what they tend to do. It's not the government, it's not the media, it's not social media, it's their local community. And therefore, we learned something about the way behavioral aspect in public health. And this is now advice we're giving, that when public policy is being formulated in public health crises, you must get the confidence of community leaders. That's the only way that you're going to get public health adherence. Okay, so that was so far about behavior. Now let's go to the next order of complexity. What about complex organs like the brain or the heart? Can they be mathematically understood? So the picture there on the left is Mikhail Gromov, who was a very famous geometer in France. He, for a long time, didn't work on anything applied, really. He's a geometer, but he got an interest in trying to apply mathematics, especially partial differential equations, to the study of the human heart. And in collaboration with researchers in New York at the Courant Institute, which is a very famous institution for applied mathematics, they were able to build a simulated heart, which is so detailed that you are now able to test interventions on it. If you give it if you inject a certain kind of treatment to the heart, what will it do? So this is a collaboration between mathematicians and medical researchers to try to produce an artificial working heart. And it seems to be successful so far, although there are still big problems to be solved. It's highly interdisciplinary, as I said, involving mathematicians, physiologists, and computer scientists. And there's still much to do in that area. Okay, now let's ask, what about the human brain? This is, of course, the topic that I really want to talk about. Okay, here is von Neumann. He's a mathematician, applied mathematician at Princeton. He was a pioneer of computing. In Princeton, even today, at the Institute for Advanced Study, if you go, there's a building called the ECP building. ECP stands for Electronic Computer Project. That building was built for him to start to design the first electronic computer. It occupied that whole building. And he was a mathematician trying to figure out, of course, this was during war times, and they were trying to figure out how to solve the problems that were coming to them from the war. But afterwards, he gave some lectures at Yale. And the lectures are been published in a tiny little book, which I advise all of you to get and read. It's called The Computer and the Brain. So in the 50s, when the computer that I have in my cell phone is more powerful than the computer he was working with, he nevertheless made some observations that are very, very prescient. That is, he was able to sort of see into the future. So he made some calculations and estimated that the brain, our brain, the human brain, is capable of performing 10 to the 15th operations per second. Now, if you think of a MIPS architecture, the architecture that's used in computers, millions of instructions per second, we don't yet have a 10 to the 9th MIPS machine. It doesn't exist yet, but yet the brain is already doing it. So from that point of view, we are all of us, each of us, carrying a supercomputer with us. So what is that about? So he analyzes what's called the nature of mathematical calculation. You see, from one point of view, our brain shouldn't work. And the reason it shouldn't work is the following. When you do a calculation, step by step, I do a calculation, and then I take the output of that calculation, do another calculation, do another calculation, do another calculation. Anybody who's done any kind of experimental work knows that, let's say it requires an observation, and you use the result of that observation in a calculation, you have to build in error. That is, if there's any error in what you've observed, it's going to show itself in the calculation. And the more times you need to do an observation and do a calculation, the errors start compounding. And after a few steps, the error will be bigger than the main term. And so the calculation will be useless. This is a common thing. Everybody in experimental sciences knows this. Now, our brain, so you may say, what is the connection of experiments and our brain? Our brain processes computation by analog machines. We don't have digital circuits implanted in our head. We use biochemical processes. There are neurons that fire, and when they fire, they need certain chemicals. And once they fire, those chemicals are depleted and they have to be replenished. So we are a biochemical computing machine, our brain is. So that's called an analog computer. Some of you may have never heard of an analog computer because by the time you were born, you're already using digital computers. But before the kind of computer you know of today existed, machines were built on analog devices. sort of biochemical, electrochemical side of devices. So the brain, therefore, being an analog machine, if I try to do a complicated calculation, after 3 or 4 steps, the error should be so much that the answer should be wrong, completely wrong. But it's not true. We do calculate very sophisticated calculations, and we get the right, I mean, we do make mistakes too, but in the end, it's possible we get the right answer. So what's going on there? What's different? The only way, therefore, his answer, von Neumann's answer is, the only way this is possible is if the brain in its own evolution has figured out already how to reduce the arithmetical depth. So instead of doing this calculation, then I use the output for this calculation, and then this calculation, and this calculation. Instead of doing 10 steps, it's figured out how to reduce it to 2 or 3 steps. And how can it do that? Well, in computer science, you know how it's done. It's called distributed computing. It's called vectorization. That's what a supercomputer is. You do vectorize the calculation. In other words, you chop up the calculation into pieces and do little pieces here and here and here and here, and then put them together. Well, somehow the brain has already figured that out, the human brain, and so we were able to decrease the logical depth. So as I said, biological calculation seems to be horizontal. We seem to have figured out our physical system seems to have evolved to a point where the arithmetic depth is small, and therefore we compensate for the defects of the analog system. For example, it said that the retina organizes images using only 3 synapses. We have billions of synapses, but it only uses three logical steps to figure out what an image is. So horizontal versus vertical computation is how the human being or how the living brain eliminates the problem of compounding errors. So then next comes the question is, how is information being propagated in the brain and in the nervous system? When neurons fire or when your nerves are firing, what are they saying? What's the language of the nervous system? What's the language of the brain? If I could put a lot of electrodes onto your brain and notice neurons firing, can I read what they're saying? What's the language of the brain? So this is the question von Neumann poses in his book. What is the language of the brain? And he sort of gives a conjectural answer. So he says logic and mathematics in the central nervous system, when viewed as languages, must structurally be essentially different from those languages to which our common experience refers. That means he's saying this is some new kind of language, totally. It's not anything that we've seen before. The mathematics we know of, in other words, the mathematics we do, may be a secondary language built on the primary language of the brain. So whatever it is, that language is that the synapses and the neurons are using, somehow the math that we're using is a derivative, not a derivative in the sense of calculus, but it's derived from that in some way. It differs considerably from what we consciously and explicitly consider as mathematics. So he's saying there's a whole new world, the whole new world of knowledge, of language, of data, of information that our brain is already doing every second of the day, and from which all that we think as knowledge is being derived. So that begs the question, what is that knowledge? What is that language? So if the language of mathematics is a derivative of the language of the brain, you can also ask about other human languages, not just mathematics. Now Chomsky, Noam Chomsky is a famous linguist at MIT, and Pinker, who was at Harvard, have been speculating on the existence of some kind of universal language or a language instinct. I don't know the merits of their speculation, but the question is, could it be the language of the brain which is universal amongst us? That is, from here, all the different kinds of human languages that we know of are expressions. Could it be? Now, as Schrödinger came to the conclusion that new laws of physics had yet to be discovered that would model the activity of living matter, von Neumann is suggesting there's a new kind of mathematics that has yet to be discovered to model neuronal activity. Once again, just as Schrödinger thought that has the physics and chemistry that you need to understand the living universe doesn't yet exist, Von Neumann is saying the math that you need to study the living universe doesn't yet exist. So what could that math be? And then, of course, we're asking this question in the context of when we're saying we're constructing living, thinking machines. This is the world of AI. And von Neumann is pointing to, you haven't even understood how the brain works. And so you're creating machines that probably can pass the Turing test, that seem living, that seem to be thinking, but we don't know how we ourselves are thinking. And it's by some other method. So it naturally brings us to the whole question of AI, which is giving, as I said, a superficial semblance of imitating human thought. If you're an optimist here, you could say maybe AI has already solved the problem of simulating human thought. I mean, given the fact that there are some people who say we don't really know what AI is doing, perhaps AI has already solved the problem of simulating human thought. And certainly, in terms of access to data, it is already has surpassed the human being. It can access more files, more papers, more information, more different sources than we're able to do in any practical amount of time. But then the question becomes, is it a tool or an adversary? Are we going to work together, or are we going to fight with each other? Are we going to become servants, subservient to AI? What is the future? So the age of AI, as I said, AI and quantum are often discussed in the same breath, but they're really very, very different. The quantum computer doesn't yet exist, and even when it is invented, when it is discovered, rather constructed, it's not likely to be a threat to us in terms of everything, every aspect of our life. But AI does have that challenge. And it's getting better very quickly, so quickly that probably any estimates that are out there are too conservative. So the different estimates are given, maybe it's about 10, 15 years before they surpass human intelligence. I remember a talk at the Fields Institute 5 years ago in Toronto, where we had an applied mathematician giving a talk, and she was saying, data is the new telescope. Well, that's true, that instead of peering into space, you look at data, and that gives you evidence or information of what you're searching for. Well, that's 5 years ago. Things have changed a lot. Today, we might say LLMs are the new research assistants. Large language models are the new research assistants. You have a telescope, which is going to enable you to see something. Well, maybe now you've got a telescope that tells you where to look. So AI is changing very, very, very fast. So it's something that none of us can afford to ignore now, whether we like it or not. Then there's this whole question about, should it be open source, should it be closed source? OpenAI, even though it's called OpenAI, is not open source. It's a proprietary technology. About $350 million has been spent in developing their large language model. And other companies are following suit, spending hundreds of millions of dollars to develop these large language models, which are the basis of their AI engines. I remember I was in 2024, I was in Shanghai. They have an annual World Artificial Intelligence Conference. So there, in fact, I was invited to speak on a panel on the future of education in the context of AI. So we talked about that. But I was listening to the talks, and speaker after speaker was lamenting the fact that OpenAI was proprietary and that we weren't able to access the technology, and it wasn't fair. This was the Chinese that was saying it wasn't fair. But 1 year later, in 2025, DeepSeek was invented. DeepSeek sort of bypassed everything that OpenAI was doing, a smaller footprint, cheaper to produce, more effective. So what's going on here? What's going on is that we really don't know what's going on, meaning AI is in too early a stage, in too much of an infancy. But we should expect all of these systems and similar systems to get better at a very rapid pace. And so this gives rise to opportunity and also concern. Firstly, as opportunity, really, I'm telling you, the race for AI is just starting. Contrary to opinions that some people express, it's not over. It's just starting. We really don't know what an LLM or an SLM or some other model really is. We don't know if the chips that exist are the right ones. We don't know if the expensive data centers are even necessary. So there's a lot here that's unknown. And when we talk about AI as an opportunity, you see technology, I started by talking about disruptive technologies. Technology, you know, a lot of the things that we're able to learn is because of technology. A lot of the great moments in human history we're able to participate in because of technology, whether it's Gandhiji's Salt March or the I Have a Dream speech of Martin Luther King, the first steps of the human being on the moon, the Nobel Prizes won by so many great thinkers, sports triumphs, women's cricket, cricket, I think, right? So they won the gold medal there. Gold medals in the Olympics, fall of the Berlin Wall. All of these things we are able to participate in, even if they happened at a time where we weren't born yet, or we were born, but it's in another part of the world. We're able to participate in and experience that discovery and that joy and that knowledge because of technology. So it has enabled huge things, and AI will be no different. It will enable huge kinds of participatory opportunities. In terms of concern, there are people like Jeff Hinton who tell us that we should stop all research in AI, that it is really too dangerous, that it may be a kind of Frankenstein. The problem is, of course, that the genie is already out of the bottle, and unlike nuclear power, nuclear energy, it's not controlled by governments. AI is already in your cell phone. It's in everybody's hands. So it's not something that's so easy to regulate, and therefore I don't know if we can follow this kind of idea of just abandoning work in AI. Probably we can't. But there is one big concern that I as an educator have, and I think all of you should have as well, namely that AI will assume an air of infallibility. We've already seen how students seem to think that if you go on Google or on Wikipedia and you find something, that's somehow gospel truth. And they'll reproduce that in their homework assignments. And unfortunately, these things have errors. So we cannot lower our guard in terms of asking critical questions. Is what I'm being told true? Does it make sense? So I think the biggest challenge for us, all of us here, is not whether we're afraid of AI or we embrace AI, but how much effort are we putting into developing our own critical thinking, because that's the thing that's going to make a difference. And then there's the whole issue of Viksit Bharat. We want to be a fully developed country by 2047. Abdul Kalam tried by 2020, he had this vision, we didn't make it. But the next goal is 2047, 1 century after independence. Is it possible? I don't think it's possible unless we use AI. It's hard to imagine reaching that goal without AI. So therefore, we really have to come to grips with this. We need to use it to enable 3 things: learning, innovation, and the management of inequality. In terms of learning, AI can be used to enable widespread learning, both formal and informal. You see, you ask, for example, how did we come to the state that we're in right now, where one person is talking to 100 people who are sitting in one place? We came to that because we didn't have the technology before to be reached everywhere. This was the only way we could find to communicate information. But even this program is being live streamed, and so there are people who are not physically present who are yet nevertheless listening to this program. So what does it mean? It means technology has made possible new paradigms for the communication of knowledge. And so we have to wonder whether we can use that in a more effective way. And then there is the fact that different students learn differently. We've all experienced this. I say something one way, and one student gets it, and the other person is perplexed. I say it in another way, and then the other person gets it, and this person may be perplexed. So why can't then we use this technology to make much more customized, more interdisciplinary accommodation for different learning styles? I think that is coming, and that's sort of very, very important. One of the first things we need to get right as AI moves forward. So we need to customize it, accommodate different learning styles, different abilities, different natural interests. And as already been stated, it has to include the humanities and the social sciences as well. We cannot say we're scientists, therefore we will not look at those disciplines. As I told you already, even when we're modeling the disease, we needed to understand behavior. Now we have sociologists in our group. We need to understand when we create a model, does it make sense from their understanding? So it has to include humanities, because I was telling some of our friends, I think the biggest health challenge in the near future is going to be suicide. And the reason it's going to be suicide is because technology is changing so much to say you're going to start asking yourself the question, why am I alive? What is my purpose? What am I doing here? The machine can do everything for me, so why am I here? What is the purpose of life? Why get up in the morning? What does it mean to be human? So things that people thought were good for armchair philosophers, a luxury to have, questions that practical people don't need to worry about, they're going to be front and center. All of us will have to come to grips with those kind of questions. What does it mean to be human? What is the purpose of life? Why do I get up in the morning? So as challenging as AI is in terms of the way it might control us, it's also forcing us to ask really fundamental questions beyond the science. And that's why we have to learn to be more comfortable with the humanities and the social sciences. AI and learning has to reach further and deeper into the population so as to provide the number and quality of original thinkers that are needed. The critical asset for us is people who can think and who can think originally, who can innovate. And we cannot say that learning is only for young people. You go to school for a certain amount of time and now your education is over. Anybody who's in the academic world knows you're constantly learning. You have to constantly expand your knowledge, revise your knowledge, refresh your knowledge. So similarly, learning has to be a lifelong process. As Sri Ramakrishna Ram has already quoted, Sri Ramakrishna said, as long as I live, so long do I learn. I have to keep learning. And that means we need to have learning opportunities for senior citizens too, for adults, for those who are retired. So a different approach to learning, which will only be possible at scale because of AI. And then there's innovation. We need new ideas. We need imaginative and original thinking. We need to be able to take out-of-the-box perspective, and we need to do it at scale. Remember the goal, you're trying to transform India by 2047 into a fully developed country. We're going to need grassroots participation. It's got to be done at large scale. So from this point of view, I would say that the challenge that people are talking about, let's stop talking about that and understand the opportunity it creates, and understand that the opportunity for innovation is huge, and the journey has just begun. And then there's the whole question of inequality. You see, inequality is an important thing because it impedes progress. I'm not talking about this from a moral or a social or an ethical point of view. I'm talking about it from a purely economic point of view. There are now enough studies by Nobel Prize winners to tell us that there's an economic price to pay when prosperity doesn't transform uniformly throughout the country, throughout the society. So there's a lot to say that. I will keep it short here. We'll talk later about the details of that. But I think this is where government is needed, public policy is needed to enable universal access to the tools that AI provides. By the way, an example of how effective public policy can be is in digital payment systems. We're all using UPI here. How is it that UPI penetrated India so quickly? If you look at the underlying technology, it's not Indian. The underlying technology, and it's well known, it's old technology, it's from the 80s. What made UPI succeed in India that now other countries are coming to India to copy, even Europe wants to copy the UPI system, is policy. The policy was there are no transaction charges. You do normally, if you do a credit card transaction or something, there will be a transaction charge. Either your bank will charge it, your credit card will charge it. UPI was mandated by government policy that there are no transaction charges. And that's why it penetrated deeply. We need that kind of policy that makes AI penetrate deeply and makes it, the tools available and accessible to everyone wherever they may be. So finally, I want to tell you about this, what I call the triangle of social growth. I've already spoke about each of the points, but I'll just repeat them. The three aspects of this triangle are learning, innovation, and inequality. Learning, I say, is the new capital. We are very, very wealthy because as long as we promote learning. When learning becomes productized, it becomes innovation. And when productization is not freely available, it leads to inequality. So we need to manage those three things. And that's the social triangle of social growth. Okay, so now I want to close up with going back to my favorite subject, namely math. So can the computer do math? Okay, AI, we talked about all the things it can do, might not be able to do, but I want to go back to proving theorems. What we do in math, can the computer do math? Well, 2 years ago, ChatGPT couldn't prove that pi is irrational. Everybody knows about pi, right? Pi is a number that occurs in mathematics. And we know that it's an irrational number, meaning in the sense that it cannot be written as a ratio of two integers. So somebody asked ChatGPT in 2023, prove that pi is irrational. The proof it gave is pi is irrational because it cannot be written as a ratio of two integers. It proved it by definition. It's not a proof. It's empty. 2 years later, DeepSeek was asked the same question. It gave a correct proof, complete proof. What's going to happen in the future? Maybe proofs are not AI's forte, in which case it's going to be our assistant. So maybe it'll be a good co-pilot, as people say, that it'll be maybe a proof verifier or an instrument for checking proofs. And one thing also in the academic world, you know, is we're faced with a deluge of literature. Every day papers are published, and you have to somehow keep up with that. So it's very hard to do, but maybe AI can be a help for us in that regard. You may say, but of all the applications of AI, why did I return to talking about its connection to math? I mean, I said, of course, it's because I'm a mathematician, but actually there's a more fundamental reason, namely math drives AI. All the technology that makes AI possible is math. And so if you can turn that around and have AI help math, it'd be mutually beneficial. It'll also probably lead to new developments in AI. So what is a realistic expectation of AI helping us to do math? Is it a graduate student, a research assistant, a junior colleague, collaborator, supervisor? What is it? We don't know. But the last thing I want to say to you about this idea of math is, we think of math, especially at the elementary stages, in terms of correctness. It's right or wrong. Did you get the right answer? But the discovery of math is not based on that. It's based on imagination. So contrary to the popular view, imagination plays a large role in the discovery of deep mathematics. Conjecture. You guess that something might be true. You speculate it might be true. And you may say, you're a mathematician. You're supposed to think rationally, logically. How can you make guesses? Well, in fact, all discovery is by guesses. As we heard in the previous talk, math is both a science and an art. And it's in that art that you find patterns which you can't explain yet. And therefore, you make guesses. So unexpected and even unintuitive connections are what gives rise to deep mathematics. You heard also, for example, Fermat's last theorem was proved by Wiles. It was open for 350 years. How did he prove it? Well, you ask, what is Fermat's last theorem? It says the Diophantine equation x to the n plus y to the n equals z to the n doesn't have solutions in integers. His proof has nothing to do with that. His proof does not touch the equation. I mean, I'm overstating it, but really, he proved Taniyama's conjecture. And now you have to trace what happened in between Fermat and Wiles's proof, how the whole problem got transformed. And so the point is that this is an unexpected connection. The Diophantine equation is something, Taniyama's conjecture, for completeness, let me state it. It says that elliptic curves all arise from modular forms. Okay? unexpected, totally unexpected. In fact, the first time that famous mathematicians heard that statement, they said it's unlikely to be true, impossible, probably implausible. And yet it turned out to be true. Not only was it true, this is the statement that Wiles proved, and it turned out to be connected to Fermat's last theorem. That is kind of unintuitive at first, connection, deep connection between things. The Hodge conjecture, another important conjecture. And now when we talk about AI hallucinating, you've all seen this hallucination. You ask ChatGPT a question and it tells you something that doesn't exist. Sometimes, I get annoyed with that. I say that, well, you see, what did you expect from AI? But part of me also wonders, is this the start of imagination? When you're children, you say all sorts of imaginary things, and people laugh, they think it's cute. The child has a good imagination. But if they continue to imagine those kind of things when they grow up, you say, well, there's something wrong. But I wonder, most of us, that's not what happens. Our imagination matures. So maybe the imagination I'm talking about is a maturing of this hallucination that we're seeing in AI now. Here is Harish Chandra, who was a very famous mathematician at Princeton. I have often pondered over the roles of knowledge or experience on the one hand and imagination or intuition on the other in the process of discovery. I believe there is a certain fundamental conflict between the two, and knowledge, by advocating caution, tends to inhibit the flight of imagination. Therefore, a certain naivety, unburdened by conventional wisdom, can sometimes be a positive asset. And you also heard about Ramanujan, lots to say there, maybe I'll miss that, I'll skip that. And finally, Einstein, who says that imagination is more important than knowledge. For knowledge is limited, but imagination encircles the world. So, my friends, as we're talking about this, we're facing big challenges, big opportunities, but let us imagine that all of this will lead to a better world. Now I lost my slide. So thank you. This is the Lodha Institute, which is a new mathematics institute that is trying to bring imagination into it.
We thank Professor Murty for a very enlightening talk, and we have time for a few questions. Can we have the mic, please? There's a question there.
So, hello? Can you hear me?
Yes.
Yeah, so you talked about the human brain functioning in very shallow arithmetic operations, very simple 1, 2, or 3 processes. But like when we train the neural networks or LLMs, it is a very deep error correcting machine basically. It performs trillions of calculations to find the predict the next word of a sort of text. Right. So isn't it a sort of contradictory way to model the human brain or the human thinking in a way?
So what I'm saying is no, because the biochemical processes are such that it couldn't be otherwise. This is what one woman is saying. In other words, it's not whether we like it or not. The human brain is doing things has found a way to work with a small level, a shallow level of arithmetic depth, but without compromising on the quality of the calculation it's doing. So it's a different model. We've built digital devices with this DeepSeek and that kind of thing, where we continue to travel along a neural network, because that's the way we know we're using digital technologies. So there are two different models for how calculation can be done. And remember also, by the way, all artificial intelligence depends on the weights that you put on the nodes, on the edges rather, that connect nodes. You change those, the whole output changes. So it's only as good as how correct you or how reasonable you were in coming up with those weights.
We have one more question here. Yeah. Debanjit.
So, sir, according to you, who is more powerful, we or AI?
So I didn't say, but I of course believe the human being has infinite potential, and so whereas the AI is still finite. So I would say the human being.
So one day, if sometimes later AI can defeat us. You're telling that.
So the question is, what do you mean by beat?
Beat us, yes.
What does it mean?
Means, sir, one day, sir, we will come in war with AI.
So you're talking about physical violence?
Yes.
So the question is then you need to figure out how to hack into those. You see, that's an easy problem actually. That's a relatively easy problem. Because if the human being who designed that AI system will know the method by which it's communicating, right? All systems can be hacked. So that's an easy, if that's all you mean, it's easy. I was wondering if you're asking a more deeper question.
Okay, sir. Yes. Thank you, sir.
Yeah, sure.
Questions, anyone? Please raise your hand or...
Yeah.
Sir, thank you, sir, for giving me this opportunity. I want to ask a question. Sir, it seems very critical that all are talking about the AI, that it could outperform the human brain. But the critical question is that if we are the creators of the AI, then how it could outperform our own intelligence? Because we invented it for our own purpose. Right. In similar way, we evolved from the nature, from the natural life. Then still we are revolting against the nature by performing various many activities like ecocide and deforestation. Then how it could be possible? Because some of the scientists believe that the AI could outperform in the year 2029. Yeah. And the scientist named Ray Kurzweil, he predicts that the AI would outperform us by the year 2045. So how it could be, sir? Sir, it raises the question on the creation and the identity of the creator.
Yeah, so the point is this, that you have to get back to the same question I was asking your colleague who asked the previous question. What do you mean by outperform? What do you mean by beating? So you have to narrow it down, because if you say, for example, who am I? Okay, am I a mathematician? Yeah, I can do math a little bit. Is that me? No, I can do other things too. Whatever list you give me of things I can do, it won't exhaust who I am, right? So when you say AI can outperform human being, in what way?
Intelligence.
What does it mean?
Sir, for example, a computer plays chess, and for example...
Okay, so let's stop right there. You have a game with a finite set of rules, right? And is able to compute strategies faster than the human being, right? Okay, so then that's a finite defined question, and it's just a matter of time before we figure out a way to do something faster. Any instance you give me when you say AI is going to do something better, you have to define it. Once you define it, it's constrained. And so you find a way to do something better than that. I mean, as you yourself said, we're the ones who invented it. For example, you say that I will create a secure system of communication. Okay? I'm the one who invented the protocol. I know where the weakness is. So I will invent a way to break that system. So those people like Hinton and others who express great concern about AI becoming very powerful and sort of taking over the world, I'll tell you what the heart of it is. The concern is that you and I, and all of us here, fail to take seriously our responsibility to ask critical questions, such as, who am I, why am I here, what is my purpose, what is the kind of world I want to live in? You stop asking those questions, you'll be overwhelmed by AI for sure. Just as many people are already overwhelmed by their cell phone. They don't think. I mean, how now it's become a problem in classes. People think that because they found it on the internet, it's true. So I told them, throw your phones in the garbage. Learn to think. Thinking is the most critical thinking. You know, you tell me something, I have to say, is it true or false? I need to figure that out, right? That is the critical thing that all of us need to develop. If you give that up, yes, computers are going to take over. It's not about what they can do. They can read 100 papers, in the time that it takes. Maybe I read one page. Fine, I'll use that as a tool. It's not going to defeat me. I'll use that as a tool. Now I can get summaries of papers from the AI. So in all of these things, you have to say, as long as you don't give up your ability to think critically, ask questions, ask fundamental questions about yourself and the world, you're not in the situation that AI is going to take over. When people worry about the future, it's because of the way we've handled technology in the past. I just told you the internet is full of amazing resources. You can learn from the greatest people that ever existed, and yet what do? We play video games. We watch movies. We become like blank minds. So the big worry, and this is why the future of education, I think, has to sort of make this very explicit. You didn't come here to learn math or chemistry or physics or biology or geography. You're here to learn how to think. And the day you give that up, you're gone. You've got to learn critical thinking. That's the one thing that no AI will make redundant. People say, coding, now coding, structured code, the AI can write faster than people, so a lot of people are out of a job. What should I do? It can't think. You can think. So that's what you've got to develop. And then it's not just about your survival, it's the survival of all of us, the world. It'll be a place where the kind of world we want to create is actually, because of these tools now, might be accessible, might be possible. So that's the challenge I leave with all of you. You've got to develop your critical thinking. You've got to figure out, here's a big problem. Let's take it a very concrete problem, 2047. It's not somebody's responsibility, it's your responsibility. How are we going to get to 2047? Start thinking, where are your ideas? And then what are the AI tools you're going to invoke to be able to make those ideas real? That's what you should be thinking about, I think. That's the challenge I give to all of you.
Okay, we have time for one last question.
It's a hand.
He was first. Maybe short, two small questions. Okay.
So regarding the misinformations available in the internet, so can AI hallucinate? And if so, is there any measure to detect that?
That's a really good question. Certainly it does hallucinate. It tells wrong things. And sometimes when you point out it's wrong, it's very apologetic. And sometimes it's not. Sometimes, no, I checked it, it's right. What I'm saying is right. So this is an area of research now. How do you deal with hallucinations? So I don't have an answer, but it's an area of research, trying to figure out what meta structures do we need to build into information by which we're able to tell that this is accurate or it's not accurate. We don't know. Yeah.
Thank you.
Can you please pass the mic to the person on your...
He's got a mic.
Yeah, you got it. Okay.
Hello, sir.
Yeah.
Actually, I had two questions, but I will just choose one for the more important one.
Yeah.
Basically, we talked about how we are using brain as an inspiration for intelligent systems. So, in Indian philosophy, lots of streams are there where there are exhaustive studies of human consciousness and brain and how it is segregated in memory. So, is there any active work that uses that as inspiration? Because I have read that there are very extensive works on how different segments like memory and different things interact together and form the whole human consciousness. So, is there any work?
So let's just be very clear about terms. Okay, consciousness is a different order of magnitude. I have to set consciousness aside. This will go only as far as mind. Okay, mind, you're right, is the antakarana. So it's got identity, it's got storage, it's got memory, it's got minding. So those things can be modeled, and they're being modeled. But whole business of consciousness is a different order of magnitude, a different problem, and frankly, I'm pretty sure it cannot be captured by this system.
So your belief is that we are not just a biological machine, there's more to us than physical?
Yeah, absolutely. I mean, fundamental to Indian philosophy is we are consciousness, and consciousness can exist independent of body and mind. I'll tell you, by the way, if I can just take a moment to elaborate on this. Philosophy is a really, really important discipline, really important discipline. It's not for asking idle questions. It can affect the whole future of a country or a world. in the East and the West, similar questions were asked, two questions. One is, do we have free will? Both East and West said yes, we have free will. Second question is, who are we? What is the human being? There the answers are different. The West said, I'm the mind. The East said, I'm consciousness, and consciousness can exist independent of the mind. Now, you may think these are just philosophical positions. Why are they important? They're important because by separating ourselves from mind, by saying we're consciousness, we put mind in the realm of nature. Nature can be studied. The whole of science is about the discovery of the laws of nature. Therefore, from the Indian point of view, the study of mind is part of science. On the Western side, I have free will, they said, and I'm the mind. Therefore, mind has no laws. Because if I'm subject to law, I don't have free will, and I'm the mind. So that's why psychology in the West developed so late. Psychology as a science is a study of the mind. But even the idea that there is a science of mind was anathema to them because they thought it violates free will. You see? So we developed the science of the mind from quite early on. Patanjali is the great teacher of the science of the mind. And the whole concept of yoga is possible because of that philosophical position. You see, the whole concept of yoga, to study the mind as a scientific discipline, as to say there are step-by-step procedure for reaching deeper and deeper levels of the mind, that whole thing is possible only because I am not the mind. You see, a philosophical position has such implications, such deep implications. But consciousness is separate, is a separate entity. Thanks. Thank you.
Okay, with that, we thank Professor Kumar Murty for a wonderful talk and a question-answer session. And I'll now like to hand over the mic to Ahan.
Thank you, Professor, for such an captivating and wonderful talk. AI is definitely the talk of the present and will be the talk of the future. Is my script generated by AI? You don't know that, and I won't reveal it. Before we conclude, a few final announcements. The entire event can be viewed on the official YouTube channel of IISER Kolkata. So if you need the slides, you can always refer to that video. Refreshment packets will be served near the registration desk. Please make sure you carry your coupons. They're required to collect your packet. We also invite you to visit the mathematical displays and other exhibits arranged by the Department of Mathematics and Statistics outside this hall. Do explore and interact. There's a lot of exciting work on display. On behalf of IISER Kolkata and the Department of Mathematics and Statistics, thank you for joining us today. Have a great afternoon. Okay. So there will be a short video that will be played. So if you can please remain seated until the video is over. It is a short video. 2 minutes. Just a 2 minutes, couple of minutes. Thank you.
Manoj, audio আছে? হ্যাঁ।
It's very important for us as a company to make sure that our success contributes in a wholesome manner to India's development. In that context, the family decided last year to donate about 1/5 of the ownership of the company to the Lodha Foundation. We have a 25 and a 50-year view, and in that context, we've realized that any nation, for it to become strong, we have to have original thinking, we have to have what's called innovation. And that is what the Lodha Institute of Mathematical Sciences is focused on.
So we're trying to actually create that ecosystem in India where high quality thinkers of mathematics, physics, computer science can get together and create the foundation for India's progress.
Because we know that in the vast history of India, there have been many great mathematicians who contributed fundamental ideas that have shaped the world that we live in today. To be a part of that tradition and to take it forward to the next level, invoking not only the expertise within India, but even that which is available around the world, it's a truly critical moment and an inspiring moment, and inspiring to be part of that.
We believe that the foundation of almost all technological progress today is mathematical. Whether it be cryptography, as I said, whether it be cybersecurity, whether it be even warfare, and definitely artificial intelligence.
I think the impact that we would like to see of LMSI is in addressing fundamental problems that are necessary to address if India is going to be developed by 2047.
So this institute is actually hoping to get the brightest researchers to come together and pursue research in cutting-edge frontier mathematics, so that the frontiers of mathematics are pushed and new knowledge is created.
And so it's going to be a welcoming place where people from all over the world can gather together and exchange ideas, gain inspiration from each other, make discoveries and advance the subject that will benefit all of us, all of humanity and all of the world.
These are very early days. We know there will be successes and there will be failures. But I can tell you that we are undoubtedly committed to making sure that in the long term, this becomes one of the leading institutions in the world.